On June 11th, 2026, a small team of researchers quietly uploaded a preprint to the online physics archive Archive, the kind of unglamorous, unpublicized posting that normally draws attention from maybe a few dozen specialists in planetary spectroscopy. This one was different. Buried inside pages of technical analysis was a single sentence that would ripple through the space science community within days. A sentence stating, in careful scientific language, that the James Webb Space Telescope had detected a wavelength of light missing from Pluto's spectrum. That corresponds to no molecule ever cataloged, not on Earth, not anywhere else in the solar system, and not on any exoplanet studied so far. Something on the surface of Pluto, nearly 6 billion kilometers from the Sun, is absorbing light in a way nothing else in the known universe absorbs light. And the researchers, after searching every published reference band they could find, came up empty. That is where this story begins. Not with speculation, but with a genuine, still unresolved puzzle sitting in freshly analyzed data from humanity's most powerful space telescope. To understand why this finding matters, and why scientists are choosing their words so carefully around it, you have to understand what Pluto actually is, how strange its history already is, and just how much James Webb has already upended what we thought we understood about this small, distant, endlessly surprising world. Pluto was discovered in February 1930 by a 24-year-old amateur astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, comparing photographic plates taken weeks apart, looking for the faint shift of a moving object against a fixed field of stars. For 76 years, Pluto held the title of the ninth planet, a distant icy world that captured public imagination precisely because so little was known about it. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, a decision that remains controversial among many scientists and the public to this day. But the reclassification did nothing to diminish how strange and compelling the little world actually is once you get close enough to study it properly. That real close look didn't happen until July 14th, 2015, when NASA's New Horizons spacecraft, after a 9.5-year journey covering more than 4.8 billion kilometers, flew past Pluto at roughly 14 kilometers per second, capturing the first detailed images humanity had ever seen of its surface. What New Horizons found stunned planetary scientists. Instead of a dead, uniformly cratered ice ball, Pluto turned out to have towering water ice mountains, a heart-shaped plain of frozen nitrogen larger than Texas, now known as Sputnik Planitia, evidence of possible ongoing geological activity, and a thin, hazy, blue-tinted atmosphere layered dozens of kilometers into space. It was one of the most consequential planetary flybys in the history of space exploration, and it left scientists with more questions than it answered, especially about that strange, persistent haze wrapping the planet. Then, in December 2021, NASA launched the James Webb Space Telescope, a joint project with the European and Canadian space agencies more than 2 decades in the making, carrying a 6.5-meter gold-coated mirror, more than 6 times the light-collecting area of the Hubble Space Telescope, tuned specifically to observe the universe in infrared light. Webb wasn't originally built with Pluto as its primary mission. Its main scientific goals involve peering at the earliest galaxies in the universe and studying the atmospheres of planets orbiting other stars. But its instruments turned out to be extraordinarily well suited to solving mysteries much closer to home, including ones New Horizons could sense but never fully explain. One of those mysteries was Pluto's haze. Back in 2017, a planetary scientist named Xi Zhang at the University of California, Santa Cruz, published a hypothesis that seemed almost too strange to take seriously at the time. Zhang proposed that the individual haze particles drifting high above Pluto's surface, composed of nitrogen, methane, and carbon dioxide compounds, cooked by sunlight into complex organic aerosols, weren't just a passive visual feature. He argued they were actively driving Pluto's climate, absorbing sunlight during the day and radiating heat away at night with such efficiency that they were fundamentally cooling the entire atmosphere, working almost opposite to greenhouse gases here on Earth. He argued they were actively driving Pluto's climate, absorbing sunlight during the day and radiating heat away at night with such efficiency that they were fundamentally cooling the entire atmosphere, working almost opposite to greenhouse gases here on Earth. If true, it would mean Pluto's atmosphere behaves unlike any other atmosphere anywhere in the solar system, cooled from within by the very particles that give the planet its haunting blue-tinted skies. Zhang's prediction was specific enough to be testable. If the haze was doing what he thought, Pluto should be emitting a detectable amount of mid-infrared radiation, a signal no instrument at the time was sensitive enough to isolate from the glow of Pluto's much larger companion moon, Charon, sitting close enough in the sky to contaminate the reading. That is precisely the kind of measurement James Webb was built to make. Using its mid-infrared instrument, known as MIRI, astronomers led by Tanguy Bertrand of the Paris Observatory pointed Webb at the Pluto-Charon system, and for the first time in the history of either world's study, managed to cleanly separate the thermal infrared signals coming from Pluto and from Charon individually. The results, published across 2 papers in April and June of 2025 in the journals Astronomy and Astrophysics and Nature Astronomy, confirmed Zhang's 8-year-old prediction almost exactly. Pluto's hazy sky is genuinely cooling the dwarf planet's atmosphere while simultaneously kicking methane and other organic molecules out of that atmosphere entirely, some of which drift across space and land on the surface of Charon itself. Researchers now describe Pluto's atmosphere as fundamentally different from anything else in the solar system, a genuinely novel type of climate system operating on a distant, sunlight-starved world that most people assumed was too small and too cold to have any weather worth studying at all. Scientists say more research into that atmosphere could eventually offer clues about the earliest chemistry on our own planet, back before oxygen built up in Earth's air, when nitrogen and hydrocarbon reactions dominated everything. That alone would have been the biggest Pluto headline of the year. Bertrand, describing the years-long effort to finally isolate Pluto's signal from Charon's interference, said the challenge had been so significant that distinguishing the two required an approach some colleagues considered borderline reckless when first proposed. But it worked, and it turned what had been a theoretical hypothesis sitting in a decade-old paper into confirmed, measured fact. Webb wasn't finished with the Pluto system. Charon, Pluto's largest moon discovered in 1978 and roughly half Pluto's diameter, has always been treated as the quieter, less dramatic sibling in the pairing, a world with no real atmosphere of its own, its surface dominated by water ice. But in October 2024, a team led by Sylvia Protopapa of the Southwest Research Institute used Webb's near-infrared spectrograph, known as NIR-SPEC, to study Charon's surface and wavelengths no previous telescope had been able to access with enough precision. They detected both carbon dioxide and hydrogen peroxide on Charon's frozen surface for the first time, chemical signatures that had evaded every previous generation of instruments studying the icy moon. Scientists have known about water ice, ammonia compounds, and organic material on Charon for years, but carbon dioxide and hydrogen peroxide had simply never been confirmed until Webb closed that gap. The detection matters because it helps researchers reconstruct Charon's formation history, and because Charon's darker reddish polar regions appear to be the direct result of methane molecules escaping Pluto's atmosphere, drifting across space, freezing onto Charon's poles, and getting chemically transformed by sunlight into the reddish organic material now visible in Webb's images, an interaction that happens nowhere else in the entire solar system. 2 worlds locked in a slow, quiet chemical exchange, one leaking its atmosphere, the other catching and transforming what lands on it, 250,000 kilometers apart, for millions upon millions of years with nobody watching until now. Then came the finding that has genuinely stumped the researchers involved, the one that pulled this story into the headlines in the summer of 2026. Every molecule and chemical element in the universe absorbs light at very specific, predictable wavelengths, a kind of fingerprint written into the physics of how electrons and bonds vibrate and shift. Astronomers use this constantly. Point a sensitive enough instrument at a distant world, examine which wavelengths of light are missing from the reflected spectrum, and you can identify, often with remarkable confidence, exactly what the surface or atmosphere is made of. It's how we know Mars has carbon dioxide in its thin air, how we identify water vapor in exoplanet atmospheres light years away, and how researchers have spent decades building an ever more complete catalog of Pluto's surface chemistry, one absorption line at a time. In the new study posted to ArXiv in June 2026, researchers turned Webb's sensitivity toward a narrow slice of the infrared spectrum that had barely been explored before on either Pluto or Titan, Saturn's enormous largest moon. Titan and Pluto could hardly be more different worlds. Titan is bigger than the planet Mercury, wrapped in a dense nitrogen and methane atmosphere roughly 50 times thicker than Earth's own, and is the only place in the solar system besides Earth known to have standing liquid on its surface, in Titan's case, lakes and rivers of liquid methane and ethane rather than water. Pluto, by contrast, is a small, deep-frozen world with an atmosphere so thin it would register as a near vacuum by Earth standards, sitting roughly 4 times farther from the Sun than Titan does, orbiting in the frigid outer reaches of the solar system, where sunlight is 1,000 times weaker than it is here at home. And yet, when the researchers examined the spectra of both worlds at a wavelength of roughly 5.11 micrometers, they found the exact same absorption lines staring back at them from 2 completely unrelated bodies, separated by more than 1 billion kilometers. The team searched through every comparable published study on planetary spectra they could find, and could not locate a single referenced absorption band that matched the location of what they were seeing on Titan and Pluto. Whatever is producing that signal has never been formally identified in any solar system world, in any exoplanet atmosphere studied to date, anywhere. The researchers were careful and methodical about ruling out the obvious explanations, before entertaining anything more exotic. If the absorption were coming from gas high in the atmosphere rather than solid material on the ground, the signal should appear stronger near the edge of each world's visible disk, where starlight has to travel through more atmosphere to reach the telescope. Instead, on Titan, the team found the opposite pattern. The signal was actually weaker toward the edge of Titan's disk, strongly suggesting the absorption originates from the surface itself, not from gas in the atmosphere above it. That is a critical distinction. This isn't some transient atmospheric haze effect. Something sitting directly on the frozen ground of both Titan and Pluto is producing a light signature nobody has ever cataloged before. What makes the finding even stranger is how differently the signal behaves on each world, details that only deepen the mystery rather than resolve it. On Pluto, the absorption line turned out to be roughly 3 times wider than the equivalent signal measured on Titan, though the depth of the absorption, meaning how much light it actually blocks, was similar on both worlds, somewhere around 4 to 5%. A wider absorption band generally suggests either a different molecular structure or a different physical state of whatever is producing it, which tells researchers the substance likely isn't in an identical form on both worlds, even if it's chemically related. And, on Titan specifically, the mystery deepens further still. The absorption line isn't evenly spread across the moon's surface. It's noticeably stronger on Titan's trailing hemisphere, the side of the moon that faces backward relative to its direction of travel around Saturn, than on its leading hemisphere facing forward. That kind of hemispheric asymmetry usually points to some directional process shaping how the substance accumulates, possibly related to how Titan interacts with Saturn's powerful magnetosphere, or perhaps tied to seasonal transport of material across its surface, though at this stage that remains an open question rather than a settled answer. So what is it? The research team floated a handful of candidate explanations in their preprint, while stressing plainly that none of them are confirmed. One possibility is benzene, a simple ring-shaped hydrocarbon, potentially mixed with some other still unidentified molecule. Another possibility involves frozen forms of acetylene, or a compound called keton, an unstable reactive molecule built from carbon, hydrogen, and oxygen. Each of these candidates is a plausible building block, given the kind of chemistry already known to occur on icy, hydrocarbon-rich worlds like Titan and Pluto, where sunlight and cosmic radiation constantly break apart and reassemble simple molecules like methane and nitrogen into more complex organic material over billions of years. But plausible isn't the same as proven, and the researchers themselves acknowledge that substantially more work is needed before anyone can say with confidence which, if any of these candidates, is actually responsible for absorbing light at that specific wavelength. As of this writing, this discovery has not yet passed through formal peer review, a critical stage where other independent scientists scrutinize the data and methodology before a finding is treated as fully established within the scientific community. That caveat matters, and any responsible account of this story has to include it clearly rather than let the mystery outrun the actual evidence. It's worth pausing here on just how unusual it is for 2 such wildly different worlds to share an unidentified chemical fingerprint at all. Titan has a thick, hazy orange atmosphere, active weather, methane rainfall, and rivers carving channels into its icy bedrock. Pluto has almost no atmospheric pressure to speak of, a surface temperature hovering around minus 230 degrees Celsius, and receives so little sunlight that at local noon on Pluto, the sun appears only as a very bright star in a black sky. There is no obvious mechanism connecting the 2 worlds directly, no shared formation history, no direct physical link between them. Whatever chemistry is producing this identical signature likely arose independently on each world, through separate but perhaps convergent processes acting on the same basic raw ingredients, nitrogen, methane, and the complex hydrocarbon soup that both worlds' atmospheres are known to generate. If that turns out to be correct, it would suggest this mystery molecule, whatever it eventually proves to be, might actually be common across cold, hydrocarbon-rich worlds throughout the outer solar system, and potentially beyond it, a chemical building block scientists have simply never had instruments sensitive enough to detect until James Webb came online. That possibility is precisely why planetary scientists are treating this finding with such seriousness rather than dismissing it as some minor spectroscopic footnote. Understanding organic chemistry on cold, distant worlds isn't just an academic curiosity about faraway ice balls. It bears directly on some of the biggest open questions in planetary science, including how complex carbon-based molecules, the same basic categories of chemistry underlying life as we know it, can form and persist under extreme cold, low pressure, radiation-heavy conditions, similar to what existed on the early Earth, and similar to conditions found throughout much of the universe. Every new organic compound identified on a world like Titan or Pluto adds another data point to that larger puzzle about how chemistry bridges the gap between simple molecules and the kind of complexity life eventually requires. There is already a mission in development that could help settle this exact question, at least for Titan. NASA's Dragonfly mission, a nuclear-powered rotorcraft lander roughly the size of a small car, is currently scheduled to launch no earlier than 2028, arriving at Titan and beginning its aerial exploration of the moon's surface around 2034. Dragonfly will carry its own onboard spectrograph capable of directly sampling and identifying chemical compounds on Titan's surface. And the researchers involved in the current mystery have specifically pointed to that mission as a potential way to finally confirm what this unknown molecule actually is. If Dragonfly manages to detect and identify the same 5.11 micrometer signature during its surface investigations, it wouldn't just resolve the mystery on Titan. It would give scientists strong grounds to believe the same or a closely related compound exists on Pluto as well, effectively using one world's ground truth data to validate a finding on a completely separate world nearly 5 billion kilometers away that no lander has any current plans to visit directly. Until then, this remains exactly what NASA and the research team involved say it is, a genuine, still unresolved chemical mystery, confirmed through legitimate instrumentation, cross-checked as best current methods allow, and not yet fully explained. It sits at an interesting moment in the broader story of Pluto exploration. In just the past 2 years, James Webb has confirmed a nearly decade-old theoretical prediction about how Pluto's haze actively drives its climate, identified entirely new chemical compounds on the surface of its largest moon, and now surfaced an absorption signature that matches nothing else cataloged anywhere in known space. 3 major findings in roughly 24 months, each one adding real, substantiated detail to a world that most people still picture as little more than a distant, forgotten ice ball demoted from planetary status 2 decades ago. What makes Pluto's case particularly compelling is the contrast between how little attention the dwarf planet gets in casual conversation and how genuinely strange it keeps turning out to be under serious scientific scrutiny. This is a world roughly 2/3 the diameter of Earth's own moon, sitting in a region of space so cold and so faint that sunlight takes over 5 hours just to reach it. And yet, it has an atmosphere behaving unlike any other atmosphere in the solar system, a companion moon actively catching and transforming its escaping gases. And now, apparently, a surface chemistry signature that doesn't match anything cataloged from decades of studying other worlds, comets, asteroids, and exoplanets combined. Every time a better instrument gets pointed at it, Pluto turns out to be stranger than the last look suggested. None of this points toward anything resembling life, and no credible researcher working on this data has suggested otherwise. What it does point toward is a genuine, still open gap in our understanding of basic organic chemistry on cold, distant worlds, the kind of gap that good science exists specifically to close, slowly, carefully, and through exactly the kind of painstaking peer-reviewed process this finding is only just beginning to go through. The preprint from June 2026 is a first step, not a final answer. Follow-up observations, independent analysis from other research teams, and eventually, if all goes to plan, direct surface measurements from Dragonfly at Titan in the mid-2030s will be what actually determines whether this is benzene, Keton ice, some form of acetylene, or something else entirely that nobody has proposed yet. For now, the story of Pluto's strange, unidentified surface chemistry sits exactly where good, honest science stories often sit, unresolved, genuinely puzzling, and worth watching closely as more data comes in. James Webb was never built with Pluto as its main assignment, yet in less than 3 years of observing this small, cold, endlessly underestimated world, it has already rewritten the basic understanding of how its atmosphere works, filled in real gaps in the chemistry of its largest moon, and now handed researchers a genuine mystery that current science cannot yet explain. Whatever this unknown molecule eventually turns out to be, the fact that it showed up identically on 2 worlds as different as Titan and Pluto suggests there is still real, fundamental chemistry happening at the edge of the solar system that nobody had the tools to see clearly until now. And that alone is a reminder of just how much remains genuinely unknown about the neighborhood we call home.